All right, continuing to work with standard error. We left off looking at these two versions of the formula. Again, it doesn't really matter. Just go with whatever the problem gives you. If it gives you standard deviation, use that one. What you're going to find is increasingly as the semester progresses, we're going to be looking at variance more and more. Remember, variance is what we use more in inferential statistics, and we start that next chapter, chapter 8. Standard deviation is used more in descriptive. So the book examples will continue to give you standard deviation for a while, but I'm going to gradually start weaning us off that in the coming near weeks here. So if we think about it, there's really only two pieces of this. The variability of the raw scores, is measured as either variance or standard deviation, and the size of the sample. So what this tells us is there are two main influences on how much error we should expect there to be between the sample mean and population mean. And the top part of this variability, we addressed this in chapter 4. The very last thing we dealt with in chapter 4 is we were talking about if the variability increases in your data, you have more error when you're looking for patterns in that data. You might recall we talked about having 10 radios tuned to 10 different stations. It's a lot of noise. It'd be a lot of error in figuring out what you're listening to. A lot of diversity can create problems in pattern recognition. So we can see that true mathematically right here, that as variability increases, the answer, the quotient, is going to increase. So that remains something to really pay attention to. So that's old news. Higher variability equals greater error. More variability, more error. Less variability, less error. But the bottom side, is about sample size. The size of your sample plays a role in error. So let's stop and think about it. Which should be more accurate? A very large size sample or a very small size sample? The larger sample is going to tend to be the more accurate sample. Imagine that I've made some soup and I'm going to have you guess what kind of soup I made. I'm going to have you close your eyes and let you sample the soup, and then you have to correctly identify what the soup is. I could either give you a teaspoon of soup or let you drink a whole cup of soup. A small sample of it or a big sample of it. Which circumstance are you going to have better odds of identifying the soup? Well, clearly with a whole cup. A bigger sample, you're going to get more of the diversity of ingredients included in it. You're going to get a more refined picture of the soup from getting a larger portion of it, if you will. So as, left off an E there, as sample size increases, error actually decreases. So variability contributes to error, but sample size, as sample size gets larger and larger, the amount of error that we're having to deal with goes down lower and lower. These are the first two pieces of what will continue in chapter 8 as what I kind of informally call the three mantras of statistics. And so we're getting the first little bit of two of those. If variability increases, error increases. And in chapter 8, we'll continue that train of logic. If sample size increases, error decreases. So it's really a good thing for you to really try to commit that to memory, because it's going to be a key component of a lot of what we do for the entire rest of the semester. As I said, we're always going to be measuring error, dealing with error, which means that these sort of logical cause and effect trains are always underpinning the work we're doing. So let's look at a couple of quick examples here. So let's say that I have a distribution of scores, and let's go with variance for this one. And let's say I know the variance for the population of scores is 20 points, and I pull a sample with 20 people in to get 20 scores for it. Well, I want to know what my standard error is. So to get my standard error, I'm going to use this formula because I got variance. So 20 divided by 20 is 1, and then the square root of 1 is 1. So what that tells me is, again, that's a measure of standard deviations. How far would I expect my sample mean to stray from the population mean just due to random chance alone? About 1 standard deviation away would be typical, is what this is telling us. Now, let's change the variability. I'm going to increase the variability to 50. I'm going to keep the sample size at 20. So what should happen? Variability is increasing, therefore error should increase. So 50 divided by 20, and then hit your square root button, and you should find that your answer rounds to 1.58. Sure enough, variability went up, as measured by variance here, and the error went up from 1 to almost just over 1.5, 1.58. So that tells us, because there's more variability in the raw data here, we have even more error. We could expect that sample mean to stray even farther away from the population mean than if we had less error. I'm sorry, less variability. Let's do 2 more for the other side. Oops, I moved my thing here. Let's go with standard deviation for this version. Let's say I have a population of scores with a standard deviation of 10 points, and I pull a sample of 25 people. So I'm using this formula, since this one uses standard deviation. So 10 over the square root of 25. 25 square rooted is 5. 5 into 10 is 2. So that tells me, based on this data with this variability in that sample size, that I could expect my sample mean to stray as far as up to 2 standard deviations away. Pretty big move. Let us now increase the sample size. So we're going to keep the standard deviation at 10. But I'm going to bump the sample size all the way up to 100. If sample size goes up, then we should expect error to go down. And so your, I wrote 100 on the top there on accident. So, because I changed both. What am I doing? Losing my mind is what I'm doing. Sorry, guys. Standard deviation stays the same at 10. Sorry. Just the sample size changes. And so 10 over the square root of 100 is 10 over 10. 10 divided by 10 is 1. So we've halved the error in the system by quadrupling the sample size. So that's measuring the standard error of the sample mean. And so, again, the calculations aren't really all that complicated. Pick whichever version of the formula you want to work with, plug it in, just make sure where you're square rooting and where you're not on those. And that's a measurement of error. That's the grand sum of what we need out of Chapter 7 in order to be successful in Chapter 8. And that's a doozy chapter coming up. So the stuff we just covered in 6 from the last set of videos, and now 7 from this one, all of that goes together into Chapter 8. So we will see you for that one. That will be quite a string of long videos, I'm sure. All right, everybody. Hope you're having a great day. You know what to do. If you've got questions, reach out. Let me know. And we'll talk to you, or I'll talk to you, in the next set of videos.